Something is happening inside dead stars that physicists cannot explain. And the closer they look, the more they suspect that the matter at the center of these objects follows rules that our entire understanding of physics was not built to handle. Tonight, we go inside, and what we find there will change how you think about everything you're made of. There are objects in this galaxy roughly the size of a city that contain more mass than our entire sun. Objects so dense that a single sugar cube of their material would outweigh every vehicle on Earth combined. Objects spinning hundreds of times per second, sweeping beams of radiation across the galaxy, with magnetic fields so powerful they would destroy the chemistry of your body from thousands of miles away. We call them neutron stars. And what is happening inside them, in the layers beneath their surfaces, in the fluid at their cores, in the deepest regions where even our best mathematics loses its footing, is one of the most genuinely unresolved mysteries in all of science. But here is the thing that really stays with me. The deeper physicists look, the more they suspect something exists in the hearts of these stars that should not be possible. Matter in a form so stable, so absolute, that if even a tiny fragment of it ever touched ordinary matter, it would convert everything it contacted. Silently, permanently. Not an explosion, not a fireball, just transformation, atom by atom, everything becoming something else forever. And the reason this matters is not just because it is strange. It is because the physics that allows this possibility is the same physics that governs every atom you are made of, the same rules that hold your body together, that keep the ground solid beneath your feet, that make chemistry and biology and everything you know about the physical world work the way it does. Those rules have a limit, and neutron stars are where the universe finds it. Tonight we are going inside, layer by layer, from the surface to the center, through every state of matter the universe creates when it pushes ordinary material past every breaking point it has. Get comfortable. This is going to take a while, and it is worth it. Before we can understand what is inside a neutron star, we need to actually understand what normal matter is, not the version from school. The version that makes what happens inside these stars genuinely makes sense. Right now, you are sitting or lying somewhere. Whatever surface you are resting on feels completely solid. It resists you. It holds you up. And your intuition tells you this is because matter is packed tightly together, full, dense, substantial. But here is what is actually happening at the level of atoms. You are almost entirely empty space. Every atom in your body, every atom in the surface beneath you, every atom in every solid object you have ever touched in your entire life is almost entirely nothing. If you took a single hydrogen atom and scaled it up until the nucleus at the center was the size of a marble sitting at the middle of a football stadium, the electron would be somewhere up in the distant stands. Everything between that marble and those stands, the entire volume of the stadium, would be empty. That is what an atom actually is. Mostly nothing. So why does anything feel solid? Why does your hand not pass straight through a table? Because of electromagnetic forces. The electron clouds surrounding atoms push back against each other. When the atoms in your hand get close to the atoms in a surface, their electron clouds repel. You feel that repulsion as resistance, as solidity, as the sensation of touching something real. Solidity is not about matter being packed tightly. It is about invisible forces between clouds of electrons creating the experience of substance. And this is the key to everything we are going to explore tonight. A neutron star is what you get when the universe finds a way to eliminate that empty space entirely. When gravity becomes so overwhelming that it crushes the vast nothingness inside atoms, forces the electrons somewhere they were never meant to go, and compresses what remains into something so dense that every intuition you have about matter simply stops working. To understand how that happens, we need to understand what creates a neutron star in the first place. We need to talk about how stars die. A star is a negotiation. From the moment it is born to the moment it ends, a star exists in a continuous tension between two forces that want completely opposite things. On one side is gravity. Gravity pulls everything inward. It never stops. Left unchecked, it would collapse a star to the smallest possible point almost immediately. On the other side is the energy released by nuclear fusion in the star's core. That energy pushes outward, creates pressure, resists the collapse. As long as there is fuel, that outward pressure holds the star up. For most of a star's life, these two forces are almost perfectly balanced. Our Sun has maintained this balance for about 4.5 billion years. Every second, it converts roughly 600 million tons of hydrogen into helium in its core. A small fraction of that mass, about 4 million tons per second, becomes pure energy. That energy radiates outward, holds the Sun stable, and we feel a tiny portion of it as warmth and light. The Sun will continue this for another 5 billion years approximately. But fuel does not last forever. When it runs out, gravity wins. What happens next depends entirely on how massive the star was. A star like our Sun will eventually swell into a red giant, shed its outer layers, and leave behind a dense remnant called a white dwarf. A white dwarf packs roughly the mass of the Sun into a sphere about the size of Earth. A teaspoon of white dwarf material weighs about 5 tons, dense by everyday standards, but nothing compared to what happens when a much larger star dies. Stars 8 to 20 times more massive than the Sun live completely different lives. They burn hotter, brighter, and dramatically faster. A star 20 times the mass of the Sun does not live 20 times shorter than the Sun. It lives roughly 1,000 times shorter. While the Sun will burn for 10 billion years, a very massive star might exhaust its fuel in only 10 million. And here is the critical difference. While the Sun can only fuse hydrogen into helium before running out of options, a massive star can keep going. When hydrogen is gone, gravity squeezes the core further until it is hot enough to fuse helium into carbon and oxygen. When helium runs out, it starts on carbon, then neon, then oxygen, then silicon. Each stage requires higher temperatures than the one before. Hydrogen fusion begins at tens of millions of degrees. Silicon fusion demands roughly 3 billion degrees, and each stage lasts a dramatically shorter time. Hydrogen burning might take millions of years. Silicon burning lasts about a day, one day. After millions of years of steadily burning through everything available, the star races through its final fuel in 24 hours, and then it reaches iron. Iron is where everything stops. Every element lighter than iron releases energy when it fuses into something heavier. That released energy is what has been supporting the star, but iron is different. Fusing iron does not release energy, it absorbs it. The moment the core fills with iron, the energy source that has supported this star for millions of years simply vanishes. What happens next takes less than a second. The iron core, no longer supported, begins to collapse under its own gravity. It falls inward at roughly a quarter of the speed of light. In about a tenth of a second, a core approximately the size of Earth, 8,000 miles across, collapses to a sphere about 12 miles across. Sit with that for a moment. An object the size of a planet crushing itself to the size of a city in a fraction of a second. No explosion you have ever witnessed, no natural disaster, no collision comes anywhere near the violence of that event. Is the most energetic thing that can happen to a single object in the universe, short of falling into a black hole. The outer layers of the star, still falling inward, slam into this newly formed ultra-dense core and bounce back in a catastrophic shockwave. That shockwave tears through the star's outer material and blasts it apart in a supernova explosion. For a few weeks, a single supernova can outshine an entire galaxy of hundreds of billions of stars. But we are not here for the explosion. We are here for what is left behind. At the center of all that destruction, where the core collapsed in a fraction of a second, sits a neutron star. During that collapse, the conditions became so extreme that the normal rules governing atomic structure simply stopped applying. Electrons, the particles responsible for those electron clouds, for the electromagnetic forces that make matter feel solid, got squeezed so hard they were literally driven into the protons surrounding them. Through a process called inverse beta decay, an electron and a proton combine and transform into a neutron and a tiny particle called a neutrino that immediately flies away at nearly the speed of light. The electron is consumed, the proton is converted. The empty space inside atoms is crushed out of existence. This happens over and over, cascading through the collapsing core until the matter is transformed from the inside out. Electrons disappearing, protons becoming neutrons. The architecture of atoms, the architecture that makes chemistry and biology and everything you know about solid matter possible, dismantled particle by particle in less than a second. What remains is a 12-mile wide sphere packed with roughly 1.5 to 2 solar masses of material in the form of mostly neutrons, no atoms, no electron clouds, no chemistry, just neutrons, squeezed so tightly that the density of the material exceeds the density of an atomic nucleus itself. That last part is worth pausing on. The atomic nucleus is already the densest form of matter we can study directly in a laboratory, the tiny marble at the center of the stadium. That is nuclear density. A neutron star is denser than that. There is almost no sentence in physics more extraordinary than that one. Let us actually go inside now, layer by layer, surface to center, because the interior of a neutron star is not uniform. It has layers, each more extreme than the last, each a different state of matter with no equivalent anywhere else in the known universe. The outermost layer of a neutron star is its atmosphere, incredibly thin, maybe a few centimeters to a meter at most, made of hydrogen and helium, heavily distorted by the magnetic field and gravity, but still technically recognizable as ordinary atomic matter. This is the most familiar part of the neutron star, which tells you something about how unfamiliar everything beneath it is. Below the atmosphere is the outer crust, extending down a few hundred meters from the surface. Atoms here have been completely ionized. All electrons have been stripped away from their nuclei by the extreme conditions. The bare nuclei arrange themselves into a crystalline lattice, a regular repeating grid held in position by electromagnetic forces between the positively charged nuclei and the sea of electrons surrounding them. Those electrons are doing something specific and important. They are obeying a fundamental rule of quantum mechanics called the Pauli exclusion principle. No two electrons can occupy the same quantum state at the same time. As they are compressed, they are forced into higher and higher energy levels because the lower ones are already filled. Those high energy electrons push outward. This is called electron degeneracy pressure. It is a purely quantum mechanical resistance to being compressed further. It is the same force that holds up white dwarfs. The nuclei in the outer crust are already strange by any earthly comparison. Ordinary iron has 26 protons and 30 neutrons. But the nuclei here have been modified by inverse beta decay, converting some of their protons into neutrons. So the nuclei in the outer crust might have 26 protons, but 50, 60, even 70 neutrons. These isotopes would be wildly unstable anywhere else in the universe. They would fall apart in fractions of a second under normal conditions. But inside the crust of a neutron star, the pressure holds them together. The environment forces stability on structures that would be impossible elsewhere. As you move deeper into the outer crust, the nuclei become increasingly neutron-rich. The ratio of neutrons to protons keeps climbing. The nuclei are getting enormous by nuclear physics standards, swollen with neutrons they would never retain under any other natural condition. And then at a depth of a few hundred meters, at a density of roughly 400 trillion kilograms per cubic meter, something critical happens. The nuclei become so saturated with neutrons that they simply cannot hold any more. There is a limit to how many neutrons the strong nuclear force can bind within a single nucleus even under these conditions. When that limit is exceeded, neutrons begin leaking out. They drip out of the nuclei, the way water overflows from an overfilled vessel. This is called the neutron drip point. It marks the boundary between the outer crust and the inner crust, and it is one of the most important transitions in astrophysics. Above the neutron drip point, all neutrons are still contained within nuclei. The matter consists of neutron-rich nuclei in a lattice surrounded by electrons. Extreme, yes, but the nuclei are still intact individual objects. Below it, the matter has three components simultaneously. Nuclei, even more bloated than before, a sea of degenerate electrons, and now a gas of free neutrons squeezed out of the nuclei, drifting through the spaces between them. Nothing in your experience corresponds to this. No laboratory on Earth can recreate it. A crystalline lattice of enormous neutron-rich nuclei, immersed simultaneously in a degenerate electron gas and a free neutron gas. Three populations of particles coexisting in a state that exists nowhere in the observable universe except inside neutron stars. As you continue deeper, the proportion of free neutrons keeps rising. 10%, 20, 50. The nuclei are dissolving from the outside, shedding neutrons into the surrounding space the way ice releases water. Except the driving force here is pressure rather than heat. And simultaneously, electron degeneracy pressure is fading. Inverse beta decay has been consuming electrons throughout, converting them and protons into neutrons. There are fewer electrons as you go deeper. The electron support is diminishing. Something else takes over. The free neutrons, increasingly dominant, begin obeying the same Pauli exclusion principle that gave electrons their degeneracy pressure. Neutrons are also fermions. No two can share the same quantum state. As the neutron fluid becomes denser, neutrons are forced into higher and higher energy levels, and they begin generating their own degeneracy pressure. Neutron degeneracy pressure. The mechanism supporting the star against gravity has shifted from electrons to neutrons at densities roughly 1,000,000 times greater than in a white dwarf. And then at the base of the inner crust, the remaining nuclei lose their identity entirely. They have grown so enormous and pressed so close together that their boundaries become meaningless. They fuse, they dissolve into the surrounding neutron fluid. No more separate nuclei, no more lattice, no more individual objects you could identify. Only a continuous ocean of nuclear matter, predominantly neutrons, stretching from here all the way to the center of the star. The atom is gone. In the truest possible sense, the architecture of matter has been destroyed. You cannot do chemistry here. You cannot have molecules. The rules that govern everything you have ever touched have ceased to apply. But before we reach that continuous fluid, something remarkable happens in the transition zone between the crust and the core. Something that I think is one of the most visually striking ideas in all of physics, and it has a wonderful name: nuclear pasta. In the inner crust, as nuclei grow and begin pressing against each other, two forces compete for control of the shape of nuclear matter. The strong nuclear force wants to pull nuclear material together into compact blobs. Electromagnetism wants to spread the positively charged protons apart. At ordinary nuclear densities, the strong force wins easily, and nuclei are roughly spherical. But in the deep inner crust, as density climbs and nuclei press together, these forces approach a balance. And when forces balance delicately, strange geometries emerge. At relatively lower densities in the transition zone, the nuclei remain roughly spherical, embedded in the neutron fluid like separate islands. The strong force holds each blob together. Electromagnetism keeps the blobs from merging. As density increases, the spheres are forced closer. At a certain point, it becomes energetically favorable for them to merge along one direction, stretching into long cylindrical tubes of nuclear material running through the neutron fluid. Physicists call this the spaghetti phase. Go deeper and the cylinders merge along a second direction, forming flat sheets of nuclear material separated by layers of neutron fluid. The lasagna phase. Deeper still, the geometry inverts. Instead of nuclear material forming shapes within the neutron fluid starts forming shapes within the nuclear material. First, cylindrical tunnels of neutron fluid running through a continuous nuclear medium, then spherical bubbles of neutron fluid embedded in that medium. Swiss cheese made of nuclear matter with the holes made of something even more extreme than what surrounds them. And then the bubbles close. The fluid becomes uniform. The crust ends. The core begins. These pasta phases are not metaphors. They are real predictions from detailed calculations using our best understanding of nuclear physics. They have genuine observational consequences. Nuclear pasta may be the strongest material in the universe, roughly 10 billion times stronger than steel, because the structures are held together by the strong nuclear force itself. The pasta phases affect how neutron stars cool after birth, how the crust deforms under stress, and why neutron stars sometimes experience sudden changes in their rotation rates that we can detect from Earth. We can see the effects of nuclear pasta in astronomical observations. We just cannot look at it directly. We are through the crust now, past the pasta, into the core. The outer core extends from the base of the crust inward for several kilometers. The matter here is a continuous fluid, roughly 90 to 95% neutrons, 5% protons and electrons maintained in equilibrium by the weak nuclear force. Why that ratio? Because the weak force keeps converting particles back and forth. Too many protons and inverse beta decay converts them to neutrons. Too few protons and neutrons decay back to protons and electrons. The system settles at a balance point where both processes occur at equal rates. At these densities, that balance point is roughly 19 neutrons for every proton. Compare that to ordinary iron, 26 protons and 30 neutrons, a ratio close to 1:1. Inside a neutron star's outer core, it is 19:1. The material has been overwhelmingly converted to neutrons. And inside this fluid, something extraordinary happens. something that sounds impossible until you understand the quantum mechanics behind it. The neutrons form a superfluid. A superfluid is a state of matter that flows with absolutely zero viscosity, no friction, no resistance whatsoever. Once a superfluid starts moving, it continues forever without any energy loss. This sounds like it should be impossible, but we observe it in laboratories on Earth. Liquid helium cooled below about 2 degrees above absolute zero transitions into a superfluid state. It climbs the walls of its container, defying gravity, creeping upward in a thin film and dripping off the outside. It flows through microscopic channels that would completely block any ordinary fluid. It has essentially infinite thermal conductivity, meaning heat spreads through it almost instantaneously. Inside a neutron star, the neutrons do this at densities trillions of times greater than liquid helium. The mechanism involves something called Cooper pairing. Two fermions, two particles that would normally be forbidden from sharing the same quantum state, can under certain conditions pair together and behave as a single boson, a fundamentally different type of particle not subject to the exclusion principle. When enough pairs form and they all fall into the same quantum ground state, the result is a superfluid. In the outer core, the attractive component of the strong nuclear force at relevant densities allows neutrons to form these pairs. When enough neutron pairs have formed, the neutron fluid becomes superfluid. We actually have observational evidence for this. It comes from something called glitches. Neutron stars are extraordinarily precise rotators. Their spin rates can be measured with remarkable accuracy using radio telescopes that detect the regular pulses of radiation they emit. Over time, they gradually slow down as they lose rotational energy, but occasionally a neutron star's spin rate suddenly jumps upward by a tiny but measurable amount. These jumps happen in seconds or less. The most widely accepted explanation involves the superfluid interior. The outer crust is a rigid solid, rotating as one body, gradually slowing down. But the superfluid interior does not have to slow at the same rate. A superfluid can only rotate by forming quantized vortices, tiny whirlpools, each carrying a specific amount of angular momentum. As the crust slows, the superfluid maintains its rotation, building up a lag between the two. Eventually, that lag becomes large enough that vortices suddenly transfer angular momentum to the crust. The crust speeds up, a glitch. The Vela pulsar, about 1,000 light-years from Earth, experiences a major glitch roughly once every 3 years. The pattern of those glitches, the slowdown, the sudden speed-up, the gradual recovery, matches the theoretical model of a superfluid interior perfectly. We are detecting the behavior of a quantum fluid from 1,000 light-years away by watching a spinning dead star stutter. Does anyone else find that almost unbelievably wonderful? The fact that we can do that at all. The protons in the outer core do something equally remarkable. They form Cooper pairs and become superconducting. Superconductivity is to electrical current what superfluidity is to fluid flow. Zero resistance. Current flows forever without any energy loss. The superconducting protons interact with the star's magnetic field in complex ways, confining it into quantized flux tubes, thin filaments of magnetic field threading through the material like an invisible forest. So the outer core of a neutron star is a superfluid neutron ocean threaded with quantized vortex lines, interpenetrated by a superconducting proton fluid carrying quantized magnetic flux tubes with a background of degenerate electrons maintaining electrical neutrality. 3 quantum fluids, coexisting in the same volume, interacting through 3 different fundamental forces, at densities hundreds of trillions of times greater than anything achievable in any laboratory on Earth. And still, we have not reached the strangest part. If you are finding this interesting and you are not already subscribed, this is probably a reasonable moment to do that. We are about to go somewhere even stranger. Let us go deeper, into the inner core, into the region where even the neutrons might not survive as neutrons. The inner core begins where densities climb above roughly twice normal nuclear density. At the very center, they may reach 5, 8, perhaps 10 times nuclear density. These are conditions so extreme that the average distance between neutrons becomes smaller than a neutron's own physical size. The particles are not just touching, they are overlapping, being compressed into the same space. When this happens, the internal structure of neutrons becomes relevant in a way that never matters under normal conditions. A neutron is not a fundamental particle. It is made of three quarks, specifically one up quark and two down quarks, bound together by the strong nuclear force. When you squeeze neutrons so close that they overlap, the quarks inside one neutron begin to interact directly with quarks inside neighboring neutrons. The identity of an individual neutron, its boundary, its distinctness as a separate object, begins to blur. This is where physicists genuinely disagree. This is where the uncertainty is real and significant. And I want to be honest about that uncertainty, because the honest version is more interesting than a confident answer we do not actually have. There are several possibilities for what exists in the inner core. The first is that the matter remains as neutrons all the way to the center, even at 8 or 10 times nuclear density. The short-range repulsion of the strong force between overlapping quarks prevents complete dissolution. The neutrons are squeezed and overlapping, but they maintain their identity as individual three-quark objects. Dense nuclear matter pushed to its absolute limit, but still recognizably made of neutrons. The second possibility is deconfinement. At some critical density, the boundaries between neutrons dissolve entirely. The quarks that were confined inside individual neutrons break free and form a sea of liberated quarks and gluons, a cold, dense quark-gluon plasma filling the innermost region of the star. Under normal conditions, quarks are permanently confined inside composite particles. We have never seen a free quark in any experiment ever conducted anywhere. If you try to pull a quark out of a neutron by injecting energy, the energy creates new quarks from the vacuum rather than freeing the one you were targeting. Confinement under ordinary conditions is absolute, but at extreme conditions, confinement can break down. We have actually seen this experimentally. When gold or lead nuclei are smashed together at nearly the speed of light at particle accelerators, the collision creates a tiny fireball exceeding several trillion degrees, and at those temperatures, protons and neutrons dissolve. The quarks and gluons break free and form a quark-gluon plasma. This has been confirmed by multiple experiments. It is real. The question for neutron star interiors is whether the same dissolution happens at extreme density rather than extreme temperature. The conditions are fundamentally different, cold and dense rather than hot and dense, and the physics in this regime is extraordinarily difficult to calculate. Our best theoretical tools for quantum chromodynamics, the theory of the strong force, have a mathematical obstruction called the fermion sign problem that makes reliable calculations at cold, dense conditions. It's essentially impossible with current methods. The question of whether the inner core contains deconfined quarks remains genuinely open. We have the theory. We simply cannot solve it in the regime that matters most. There is a third possibility that deserves careful attention, because this is the one with the most striking implications. There are 6 types of quarks: up, down, strange, charm, bottom, and top. Ordinary protons and neutrons are made only of up and down quarks. The strange quark is heavier than the others, but not enormously so. At the densities found in the inner core, the energy levels of up and down quarks get forced extremely high by the Pauli exclusion principle. All the lower energy states are occupied. Adding another up or down quark means placing it in a very high energy level. At some point, it becomes energetically cheaper to produce a strange quark, which starts filling its own empty lower energy levels, than to add another up or down quark to an already crowded distribution. The system lowers its total energy by spreading quarks across 3 flavors instead of 2, even though strange quarks are individually heavier. More like having 3 half-full containers than 2 overflowing ones. If this happens, the inner core contains strange quark matter, a roughly equal mixture of up, down, and strange quarks. And here is where things become genuinely remarkable in a way that touches questions much larger than neutron star physics. In 1984, a physicist named Edward Witten proposed something that sounds simple but has extraordinary implications. He suggested that strange quark matter might be the true ground state of matter. The ground state of matter means the lowest possible energy configuration, the most stable arrangement that matter can take. Right now, we believe ordinary iron is the most stable form of matter per particle. Iron sits at the bottom of the nuclear binding energy curve. You cannot create something more stable than iron through ordinary nuclear processes, which is why iron is what stars produce at the end of their fusion cycle. But Witten's hypothesis says iron is not actually at the bottom. Strange quark matter, a 3-flavor mixture of up, down, and strange quarks in a free state might represent a genuinely lower energy configuration than iron, than any ordinary nuclear matter, than anything chemistry can create. If that is true, then ordinary matter, the protons and neutrons that make up everything around us, every rock, every ocean, every planet, is metastable, not truly stable, trapped in a higher energy state, unable to convert to the true ground state because the conversion cannot start spontaneously, like a ball resting in a shallow bowl on top of a hill, stable enough in practice. It will not roll anywhere without a push, but not at the lowest possible energy position that exists. Your body in this picture is somewhat like a diamond. A diamond is metastable relative to graphite. Graphite has lower energy. A diamond should technically convert to graphite over time, but there is an energy barrier between them that is enormous under normal conditions. So the diamond stays a diamond essentially forever. Ordinary matter might be the same, metastable, prevented from converting to strange quark matter by an energy barrier, stable for all practical purpose, stable for the entire age of the universe, but not in the absolute lowest energy state the laws of physics allow. Now, here is the part that physicists take very seriously. If strange quark matter is the true ground state, and if it is stable at low pressures rather than only under extreme neutron star conditions, then a small fragment of strange quark matter brought into contact with ordinary matter would catalyze a conversion, not through an explosion or a violent collision, but simply because ordinary matter, touching the lower energy form, would find it energetically favorable to convert. Atom by atom, particle by particle, everything in contact with the strange quark matter would become strange quark matter. These hypothetical fragments are called strangelets, chunks of strange quark matter ranging from tiny, smaller than an atomic nucleus, up to macroscopic lumps. If they exist, and if strange quark matter is truly the ground state, a strangelet would not react chemically in any ordinary sense. It would not burn. It would not explode. It would simply grow, absorbing and converting ordinary matter until it ran out of material or some other process intervened. The implications of this applied to a planet are worth thinking about carefully, not as a cause for alarm, but because the physics itself is what physicists call a serious open question, not science fiction, a genuine theoretical possibility that cannot currently be ruled out. I want to be clear about where the uncertainty sits. We do not know whether strange quark matter is actually the ground state. Witten's hypothesis is theoretically motivated but unconfirmed. Calculating whether it is correct requires solving quantum chromodynamics in a regime where our mathematical tools fail. Different theoretical approaches give different answers. The question is genuinely open. We do not know whether small fragments of strange quark matter, strangelets, would be stable at low pressures even if bulk strange quark matter is stable. The stability of large quantities is one calculation. The stability of small fragments is a harder and separate question. We do not know whether strangelets are produced in neutron star collisions in significant quantities or whether they survive if produced. What we do know is that when heavy ion colliders began accelerating heavy nuclei to near light speed, there were genuine scientific discussions in peer-reviewed journals about whether the collisions could produce stable strangelets. The conclusion was that even if strangelets exist, the conditions in those particular collisions would not produce stable ones because the temperature would be too high. But the conversation happened. It was taken seriously. The physics required it to be. And somewhere in this galaxy right now, neutron stars are colliding. Two neutron stars spiraling into each other, drawing closer over millions of years, their final inspiral radiating gravitational waves across the universe. When they collide, the densities and pressures at the collision point exceed anything inside a single neutron star. If conditions for strangelet production exist anywhere in nature, a neutron star merger is probably the most likely place. Whether those strangelets survive, whether they travel through space, whether any of them are heading in any particular direction, we do not know. That is an open question in physics right now. We actually witnessed a neutron star merger in 2017. The event was designated DW17081. On August 17th, gravitational wave detectors at LIGO and Virgo detected the signal from two neutron stars spiraling into each other and colliding, approximately 130 million light-years away. Within seconds, alerts went to observatories around the world. Within hours, more than 70 telescopes on every continent and in space had turned to observe the aftermath. It was the first time a cosmic event had been observed in both gravitational waves and light simultaneously, one of the most important astronomical observations in human history. The gravitational wave signal during the final inspiral, when the two stars were still separate and drawing closer, carried information about how much each star deformed under the tidal force of the other. A star with softer interior matter deforms more easily. A star with stiffer interior matter barely deforms. This deformation leaves a distinctive imprint on the shape of the gravitational wave signal. What LIGO measured was consistent with moderately stiff neutron stars. Neutron stars that do not compress too easily. This ruled out certain theoretical models while supporting others. It did not answer the question of what exists in the core, but it narrowed the possibilities in a meaningful way. The electromagnetic observations that followed were equally remarkable. The merger produced a kilonova, a thermal glow powered by the radioactive decay of heavy elements freshly created in the explosion. Spectroscopic analysis confirmed the presence of strontium and likely other heavy elements, rare earth materials, that can only be created in environments with enormous neutron fluxes. The gold in any ring you might own, the platinum in a piece of jewelry, the uranium in a nuclear reactor. All of it was created in a neutron-star collision somewhere in the history of the universe, scattered into space, incorporated into the gas cloud that eventually formed our solar system, and concentrated in Earth's crust over billions of years. Everything heavy and precious in the physical world was forged in the collision of dead stars. How do we actually learn about neutron star interiors, given that we cannot visit them, cannot recreate their conditions, and have mathematical tools that break down in the relevant regime? The answer is observations, applied with extraordinary care. The most direct constraint comes from mass measurements. If we can measure how massive a neutron star can be, we immediately eliminate any theoretical model predicting a lower maximum mass. A softer equation of state, meaning matter that compresses more easily, supports less mass before the star collapses into a black hole. A stiffer equation of state supports more. One technique for measuring neutron star masses uses something called Shapiro delay. A pulsar in a binary system with a white dwarf emits radio pulses with extraordinary regularity. When the white dwarf passes between us and the pulsar, the radio signals have to travel slightly deeper into the white dwarf's gravitational field and arrive slightly late by a precisely calculable amount depending on the geometry of the system. By measuring this delay precisely, you can calculate the masses of both objects. Using this technique, the neutron star PSR J0348 plus 0432 has been measured at roughly 2 solar masses. PSR J0740 plus 6620 has been measured at about 2.1 solar masses. These numbers immediately eliminate any equation of state predicting a maximum mass below about 2 solar masses. NASA's Neutron Star Interior Composition Explorer, known as NICA, is an X-ray telescope mounted on the International Space Station and specifically designed to measure neutron star radii with unprecedented precision. By analyzing the pattern of X-ray emission from hotspots on the surfaces of rotating neutron stars, accounting for how the star's gravity bends and distorts the light, NICA can determine both the mass and the radius of the same object simultaneously. NICA's measurements suggest neutron star radii of roughly 12 to 13 kilometers for stars of about 1.4 solar masses, consistent with a moderately stiff equation of state, not too soft, not too hard. The combination of mass measurements, radius measurements from NICA, and tidal deformability measurements from GW170817 constrains the equation of state substantially more than was possible a decade ago. Not enough to answer the central question definitively. Not enough to say with certainty whether quarks are free at the center, but enough to eliminate a large fraction of the theoretical possibilities. Future gravitational wave observatories will do much more. The Einstein telescope planned for Europe and Cosmic Explorer, proposed for the United States, will be roughly 10 times more sensitive than current detectors. They will observe neutron star mergers not at a rate of 1 per several years, but potentially hundreds per year. Each merger provides another measurement of tidal deformability. With enough events, the statistical power will be sufficient to distinguish between models with and without quark deconfinement in the core. We may be, within a generation or two of physicists, able to answer the question of what actually exists at the center of a neutron star. I want to say something about that prospect, because I think it is genuinely worth appreciating. We are, using radio telescopes and gravitational wave detectors and X-ray satellites, learning about the behavior of quarks in a regime no particle accelerator can reach. The universe built a laboratory we could never construct ourselves, filled it with conditions we can never recreate, and placed these laboratories across the galaxy in the form of dead stars. And we have become clever enough to read them, not by visiting, not by touching, but by catching the radiation they emit, measuring the ripples in space-time from their collisions, timing the pulses of their rotation with precision that rivals atomic clocks, and decoding from all of that the structure of matter at the most extreme conditions the universe produces. A neutron star begins as an ordinary massive star. It burns for millions of years. It builds the elements, fusing hydrogen into helium, helium into carbon, carbon into oxygen and neon, on through the periodic table, building the atoms that make up planets and people and everything physical. When it finally reaches the end of its fuel cycle, it dies in a supernova, scattering those elements into space. The calcium and iron and oxygen and carbon that are in you now were inside a star at some point in the history of the universe. The gold and platinum created in neutron star collisions scattered into the interstellar medium, incorporated into the cloud that formed our solar system, concentrated in the crust of this planet over billions of years. And what remains after the explosion, that 12-mile sphere of matter at the edge of what physics can describe, keeps rotating, keeps radiating, keeps carrying in its interior the record of what matter does at the absolute extreme. Information encoded in how it spins, how it deforms, how it cools, how it occasionally stutters in a glitch, how it emits gravitational waves in its final collision. Information we are only now learning to read. There is something I want to ask you before we finish, because I am genuinely curious about your perspective on this. Given everything we have covered tonight, the possibility that strange quark matter might be the true ground state of matter, the possibility that strangelets could in principle exist and travel through the galaxy from neutron star collisions, the fact that this is not ruled out by current physics but simply unknown, does that change anything about how you think about ordinary matter, about the atoms around you right now? I have been sitting with this question for a long time, and I still find it difficult to fully resolve. On one level, it is pure abstract physics, so remote from everyday experience that it barely registers. On another level, it is a statement about the nature of everything physical, that the matter we are made of might be in a higher energy configuration than the absolute minimum the universe allows, and that there is something more stable than iron, more stable than atoms, more stable than anything chemistry produces, and we simply do not know whether we will ever encounter it. Let me know your thoughts in the comments. Genuine questions about the physics, things you want to understand better, or things that were not explained clearly enough, are genuinely useful for working out what to cover next. And if you are watching this and you have been finding the channel worthwhile, there is a Patreon linked in the description where you can support it directly if that feels right to you. Even small contributions make a meaningful difference in being able to keep making videos like this one. The next video is already being put together. We are going somewhere equally strange. I will see you there.